Hello everybody! We present the new feature of our WebVectors toolkit. The WebVectors service computes semantic relations between words. Semantic vectors reflect meaning based on word co-occurrence distribution in the training corpus, which is a huge amount of raw linguistic data. We currently support services for English, Russian, and Norwegian languages. Until recently, exploration and visualization of semantic vectors was limited to so-called static word embeddings, that is, architectures like WebVectors or fast text. But we decided to keep up with the recent advances in distributional semantics and introduce contextualized embedding architectures, namely ELMo. Why ELMo and not transformer-based architectures? Because it was shown that ELMo can often outperform transformers like BERT or be on par with them, while requiring significantly less computational resources. We believe it is especially important for teaching-like activities and also simplifies our deployment logistics. For analyzing ELMo representations of an arbitrary input phrase, we offer the metaphor of a two-dimensional text. Now let's move on and look at our service in more detail. The service itself is quite simple. A user enters an input phrase, typically from 5 to 15 words. We allow the user to choose the exact ELMo layer from which token representations will be inferred, because different neural networks layers convey information related to different linguistic tiers, syntax or semantics or pragmatics, etc. At this point, we can choose between the top ELMo layer and the average of all layers. Let's stick to the top layer only. Now we produce contextualized token embeddings for each token in the query and find the top words in the time embedding model which are closest by cosine similarity to each of the token embeddings. These predictions are lexical substitutes. They demonstrate what other words could fill these positions in the query, depending on the context. Both the words from the input sentence and the lexical substitutes are colored according to their frequency tier in the reference corpus: green for high, blue for mid, and red for low frequency, in accordance with other WebVectors components. The font size of the lexical substitute corresponds to cosine similarity between the token embedding and the substitute type embedding. Thus, we can instantly see which word tokens the model is unsure about. In this example, the model was not so sure about the neighbors for the word apple, while the neighbors for the words tasty and fruit for more sound. Each word is hyperlinked to the landing page, where we can see additional information about it, namely the graph, the lexical graph, some information from the Wikipedia, the neighbors in the static model, and also we can search this word in the other models. Also, we keep a history of substitute queries. So if we add something more to our query, we can study the changes brought by different context or a different word order. For example, let's try and make the neighbors of the word apple more sound. For example, let's say we input this phrase. We can see that the neighbors for the word apple now are in the bigger font, which means that the model is more sure about them. We hope that the new functionality will provide language teachers and NLP researchers with a powerful tool to study word meaning and context, and at the same time keep our audience up to date with recent advances in the field of distributional semantics and deep learning-based NLP. Bye!